Hi everyone, welcome back. In this lecture, we're going to be talking about qualitative matrix stability. So these are going to be some shortcuts you can use to figure out whether or not an equilibrium is locally asymptotically stable. That sometimes work, but don't always work. So let's go ahead and get started. I should put this in notebook mode. Okay, so first I'm going to define a sine function. I mean SIGN, not SINE. So the sine function, sine of x is going to be equal to either plus, minus, or 0. It's plus if x is greater than 0, minus if x is less than 0, and 0 if x is equal to 0 for any x in the real numbers. Okay, and a couple of conventions. First, sine of a matrix or vector, let's say A11 through A1n, a m1 through a mn. So for any matrix or vector, it's just going to be the component-wise sign. So just going to apply it to every one of the entries. M1 through sine amn. Okay, so to give an example, sine of 1, 3, minus 1, 0 is equal to plus, plus, minus 0. And let's also use the convention that minus sine of x is equal to sine of minus x. So this implies that minus plus is equal to minus, minus minus is equal to plus, minus 0 is equal to 0. Okay, so having defined the sine function, which should be fairly straightforward, let's define a sine pattern. So, define qualitatively locally stable based on the sine pattern. So if you have a square matrix, J, whose sine pattern, so sine of J is equal to some matrix Q. So then the square matrix J is qualitatively stable. Qualitatively stable if all matrices with the same sign pattern, Q, have eigenvalues with negative real parts. Okay, so sometimes it'll turn out that just by looking at whether the entries are positive or negative, you can immediately tell that all the eigenvalues have negative real parts, which would imply that it's locally asymptotically stable. That an equilibrium with that as the Jacobian would be locally asymptotically stable. So for example, if we have the matrix J is equal to minus 3, 1, 0, minus 1, well, that implies that Q is going to be equal to minus, plus, 0, minus. But now, this is qualitatively asymptotically stable because we know that with a triangular matrix, the eigenvalues are just all the diagonal terms, and all the diagonal terms here are negative. So this implies that this is qualitatively asymptotically stable. Qualitatively stable, which implies that it's locally asymptotically stable. Yeah, because of these diagonal entries. So important to note that qualitatively asymptotically stable implies locally asymptotically stable, but not the other way around. Qualitatively stable implies locally asymptotically stable, but not the converse. So sometimes you'll be locally asymptotically stable, but you won't be qualitatively stable. So this is qualitative stability is a sufficient but not necessary condition for local asymptotic stability. But it is a useful shortcut because sometimes it's a lot easier to figure out whether or not something is qualitatively stable than actually just using, say, Routh-Hurwitz. So often easier than Routh-Hurwitz or Gershgorin circle theorem. So it's often easier, but it's just another tool in your toolbox. Okay, so having said that, in order to do this, you still need to compute a Jacobian matrix in order to find the sign, right? So luckily, it turns out that in a very particular set of differential equations, the Jacobian matrix is very easy to compute for any positive equilibrium. Or rather, at the very least, the sign of the Jacobian matrix is very easy to compute for a positive equilibrium. So we're going to talk about a Locovatera predator-prey system. So generalized Locovatera, where you have some predators that are eating up some prey animals in some complicated interaction system. So this is going to be, let's go ahead and define this. So a system of differential equations. Equations having a specific form. So it's a form that's going to be almost affine, but not quite. So like linear-like, but not quite. So this is dxi. dt is going to be equal to xi times ai naught plus the sum from j equal 1 to n of aij xj for i equal 1, 2 through n. So this system is known as a Locovatera system. Volterra system. And this is often used to study predator-prey interactions. Notice that the aside, dxi dt equal to just ai naught plus the sum from j equal 1 to n aij xj. So if you remove that term, then this is affine, because which is to say you can rewrite it as which is to say that you can rewrite the system. Actually, let's go ahead and rewrite the system in a slightly different way. So aside, we can rewrite this. Let's say equivalent. Rewrite, because putting this in matrix form will make life a little bit easier. So that is x dot is equal to, and this is going to be a diagonal matrix. Actually, let me draw this all out. This is going to be a diagonal matrix with x1 through xn, zeros everywhere else, times, this is going to be, we have our ai naughts, so a1 naught, a2 naught through a n naught, plus, and this is going to be another matrix, which is going to be a11 through a1n, a n1 through a nn, times the x vector, x1 through xn. Let me go ahead and rewrite this as x1 dot xn dot. Okay, so what you'll notice is that if you take a look at each of the rows here, so this top row is the summation a11 through, is this summation, this times this, which is going to give you this term here. So you get that term by multiplying that out for a particular xi, and then you add it to this term here. And you multiply everything in that row by xi. So you can rewrite it in this form, and you'll notice that it's almost affine. So this is almost affine. And I'm going to go ahead and call this matrix A, so the interaction matrix. Since this encodes the interactions between each of the various species. And of course, this is just x. And I'm going to call this particular vector minus b for reasons that will become apparent pretty soon. And this, you can think of this as diagonal of the x, and this here is x dot. Okay, so this is rewriting in matrix form, which is a little bit nicer to understand. And so from this form, you can pretty quickly figure out the equilibria. So the first thing is that 0 is an equilibrium. And this is because, well, if x is equal to 0, then the diagonal matrix that has x along its points is also 0 matrix, and so you get 0. So this should be pretty easy. You can just plug in that, and you'll find that that's an equilibrium. Also, you have that x bar is an equilibrium if we have that a x bar is equal to b, right? Because if you look at this this term over here on the right, if ax bar is equal to b, then that entire term is just going to be the 0 vector. So that is also an equilibrium. So now, if the determinant of a is not equal to 0, then x bar, which is equal to a inverse b, is a unique positive equilibrium. So it turns out that this will be the only equilibrium that is strictly positive for if the determinant is equal to 0, or not equal to 0. So if the matrix is invertible. So and if x bar, so let's rewrite x bar is equal to x1 bar, xn bar transpose is greater than 0. So if all the entries are positive, then it turns out that the Jacobian of the matrix at x bar is precisely equal to the diagonal matrix of x bar times a, which is equal to x1 bar a11 through x1 bar a1n down through xn bar an1 through xn bar ann. Okay, and that you can just use the definition of Jacobian and take the partial derivatives, and this will fall out. I'm not going to walk through that, but that is pretty straightforward. And so, in this particular case, for a positive equilibrium x bar, we get a really nice fact, which is that Q which is equal to the sine of the Jacobian matrix, is also equal to the sine of A, because we assume that that was strictly positive. So all xi bar are strictly greater than 0. So this is true for a Locovatera system. And this is super nice, right? Because it means that you don't have to do, you basically don't have to do any computation to figure out what the sign matrix of the Jacobian at any positive equilibrium is. So, and of course, it's the positive equilibrium that we care more about, because the 0 equilibrium where all the species die out is uninteresting. And of course, if you're thinking about the 0 equilibrium, There might be equilibria where only some of the species have died out, but without lots of generality, you can then rewrite the system to only have the species that haven't died out for the equilibrium. And so you can use this to very quickly figure out qualitative matrix stability for a Lotka-Volterra system at a positive equilibrium. So let's go ahead and give an example of this, per usual. So this is example 5.23 in the textbook. So consider a one predator, two prey system. So maybe you have a species of wolves that's eating both deer and sheep, let's say. And we can write the system as dx1 dt is equal to x1 minus a1 naught plus a12 x2 plus a13 x3 dx2 dt. So this is a particular system I'm just writing out here. Let's see, a2 naught minus a21 x1 dx3 dt is equal to x3 times a3 naught minus a31 x1 minus x3, where we're going to assume that all the coefficients a, I, j are greater than 0. And that's why I wrote some of those with negative signs. So basically I'm deliberately encoding in the negative interactions. So when a positive equilibrium, x bar must satisfy this matrix. So this is 0. And then we have the a12, a13, minus a21, 0, 0, minus a31, 0, and minus 1, times x1 bar, x2 bar, x3 bar, which is equal to, we take the negatives of all the coefficients there, so this is a1 naught, minus a2 naught, and minus a3 naught. Or if you expand this out, you'll see that what you get is x1 bar is equal to a2 naught, a21, which is always greater than 0. And x3 bar from the third line is equal to a3 naught minus a31 x1 bar, and x2 naught is equal to a1 naught minus a13 x3 bar over a12. So therefore, x bar is positive if we know that x2 bar is greater than 0 and x3 bar is greater than 0, since x1 bar is always positive. Okay, so now let's assume that that's true. Assume x bar is greater than 0. Then q is equal to the sine of j, which is equal to the sine of our interaction matrix A up there, which is equal to 0, positive, positive, minus 0, 0, negative, 0, negative. So, of course, now we've gotten to this point, and now we can say, well, if all matrices that have the sign pattern have negative real parts, then you're locally asymptotically stable. But, of course, that's also non-trivial to do. So I'm going to give you a bunch of conditions that, if all these conditions are true, then, a bunch of conditions that are related to whether or not this matrix is qualitatively qualitatively stable. And to do this, we're going to have to introduce a new concept, which is I'm going to introduce a signed digraph, and write as a signed digraph, which is related to the graphs, the life cycle, which is sort of similar to the life cycle graphs we saw back in chapter 1, a little bit different. So here I'm going to call lists x1, x2, and x3, x1, x2, and x3. And so I have x1, x2, x3. And like the life cycle graph, I'm going to draw an arrow for each column. I'm going to draw an arrow from that node to all the other nodes in that column. So let's see, list here is going to be minus and minus. And let me actually put this in a different color just so that it's a little bit more obvious. Let's make those purple. And so those are going to be, x2 is going to have a positive to x1, so positive. And that's it. And let's make these orange. So there's going to be a positive to x1, and I have a negative self-loop. So the idea here is just to draw n nodes and draw an edge xi to xj positive if aij is greater than 0, and xj to xi, or sorry, xi to xj negative if aij is less than 0. Okay, so now that we have all these things, let's go ahead and give a theorem that gives some necessary conditions for qualitative stability based on these matrix entries, and we can rephrase it in terms of this Sine digraph. So these are necessary conditions for qualitative stability. So if we have let J is in an n by n matrix, is qualitatively stable, and of course Q is equal to sine of J is equal to some matrix Qij of sines, then we need all these conditions. The first is that Qii is less than or equal to 0 for all I equal 1, 2 through n. And so of course these are the self loops, right? So these are so this condition is just saying no positive feedback loops. So if you draw an arrow from a node to itself, it can't be positive. It can be 0, in which case you don't draw an arrow, or it can be negative, but it can't be positive. And Qii is strictly less than 0 for some I. So at least one negative feedback loop. Condition 3 is going to be that the sine of Qij has to be equal to minus the sine of Qji. So if you have an arrow going from node I to j, from node I to node j, then you have to have an arrow going the other way with the opposite sign. So if you have nodes that are interacting, you must have opposite signs. Opposite signs for interacting nodes. 4, given a sequence, so this is going to be a path. So given a sequence Q, let's say I0, I1 through Q, let's see, Q I1, I2 through Q IR, I0. So that returns back to the beginning. So a path returning to the original node. Returning to the original node. So given a sequence like that, that contains 3 or more distinct indices, I0 through IR, at least one of the elements just a moment. Sorry, as I was saying, at least one of the elements must be 0. So Basically, what this is saying is that we have no cycles. Let me rephrase this. Let me containing R containing R plus 1 greater than or equal to 3 or more distinct indices. So basically, if you have you can't go around in the cycle. And so I realized that the other way of phrasing was a little bit unclear whether you only need 3 distinct indices or all of these are distinct indices, and this is the path of links of these 3. So if you have 3 distinct nodes basically in your graph, and you go around in the cycle, well, at least one of the elements must be 0, so you can't actually go around in the full cycle without hitting a lack of an edge. And lastly, I'm just going to assume that the determinant of J is not equal to 0. So this is hyperbolic. So this is one of the conditions, but note we will often just assume this condition. Because otherwise, you do have to check that, but it's sufficiently different from all the other methods we're using for checking that we're just going to assume this to be true for the most part, unless I tell you otherwise. I'll try to be clear about that every time we use it. Okay, so now that we have that, these are necessary conditions. So if it is qualitatively stable, then all these conditions must be true. Let's also give a sufficient condition, which is going to be a little bit complicated to define, so I'm going to have to give a couple definitions first. So a predation link is a pair of nodes connected by edges going in opposite directions with opposite signs, opposite non-zero signs. Okay, what do I mean by that? So if we have xi and we have xj, then there's the predation link if you have a plus in one direction and a minus in the other direction. And a predation community is a maximal subgraph consisting, by maximal we mean that it can get no bigger, of all connected predation links. So you can just think of this as a connected component of the graph, except we're working with, since we're working with these Sine digraphs, this is just basically we're just defining a connected component, and we're calling it a predation community because these are the communities of organisms that eat each other, basically. And let's see, this is definition 5.9. And once we've defined this, then we can now define a color test. So we're going to color each node with a negative feedback loop gray, or purple. I'm going to use purple since it's a little bit easier for me to show purple than it is gray, but just some color, and all other nodes white. The color test is 1. There exists at least one white node. 2. each white node is connected by a predation link to at least one other white node. And 3, each gray node, or purple, since I'm using purple here, is connected by a predation link to, so each gray node that is connected by a predation link to a white node is also connected by a predation link to at least one other white node. Okay, so this is basically saying that if you have a purple node here, if it's connected to a white node, then it also has to be connected to another white node. Okay? And this one here is saying a white node is connected to at least one other white node. And this is just saying you have a white node. And now let's us give a theorem, which is, and you should be careful because this theorem will say that if it fails the color test, then something is true. So we're going to let Q be equal to sine of J is equal to Q ij, so standard setup. If matrix J satisfies the 5 necessary conditions in theorem 5.12, and if in addition each predation community fails at least one of the color test conditions then J is qualitatively stable and therefore locally asymptotically stable. Qualitatively stable. And note that this is if it fails. So it has to satisfy the 5 necessary conditions and it has to fail one of the color test conditions. So let's give an example of this. I'll give a couple examples actually. So first let's go back to our example that we were doing earlier. So we have our x1, we have our x2, we have our x3. And let's see, what were the arrows? Plus, minus. So minus, this was a plus, and we had a minus here. So because this has a negative self-loop, we know that this is a purple node. Or a gray node. So now the question is this qualitatively stable? So first, let's check the 5 necessary conditions. So note, no positive feedback loops. 2. So we have at least one negative feedback loop. That's true. That's this x3 here. 3. Well, all non-self loops come in opposite sign pairs. So that's also satisfied. 4, well, we have no cycles. And 5, assume that J is the assume determinant of J is not equal to 0. Cannot tell from graph. Or may not be able to tell from graph. Sometimes you can, but often cannot tell from graph. Well, let me put this in a box because this is a just mention this assumption. Okay, so long we're going to assume that to be true, but we'll note that here this fails color test condition 3 because the gray node only connected to one white node and not another. So because it fails the color test and satisfies the 5 conditions, necessary conditions, this implies that J is locally qualitatively stable, which also does imply locally asymptotically stable. J is qualitatively stable. If the determinant of J is not equal to 0. Okay, let's go ahead and give another example. So this is going to be a little bit more complicated. I'm taking this from the book, but I'm going to ignore some of the biology related to it. It's basically a host-parasite model where we have 3 different parasites for 3 different host life stages. So this is going to be 0, 0, 0. We're going to have, let's see, 1, 2, 3, 4, 5, 6. It's going to be plus 0, 0, 0, plus 0, and 0, 0, plus. And this is going to be minus 0, 0, 0, minus 0, 0, 0, minus, and minus, 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 plus, 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 0, 0, 0, where these are the host stages or the parasite stages. So this is parasite 1, parasite 2, parasite 3, host 1, host 2, host 3. And you can pretty much ignore it, except that this is going to be the labeling of the, so given this particular Sine matrix, which arises from some model of host-parasite interactions, which we're not going to worry about so much now, let's go ahead and draw the digraph. So we have P1, P2, P3, and let's say we have H1, H2, and H3. Okay, well, if you start drawing out all these arrows, you'll find that we have these plus or minus arrows. And we have a self loop here, which is negative, and a positive arrow, and a positive arrow, a self loop, which is negative, and a self loop, which is negative, as well as a positive arrow this way. So note that this is not qualitatively stable, and this is immediately obvious for a couple of reasons, but the one I'm going to list here is because of closed loop. So if there are any closed loops here, then you can't be qualitatively stable. Also, unpaired interaction arrows. So this is not qualitatively stable, and you can immediately tell by just looking at these conditions. Okay, thank you very much. That is all for this video, and I will see you next time.